Carol Moreno, and these are Kevin Goldberg and David Cardenas. And today we'll be talking about our senior project on a dynamometer testing for aircraft air turbine starter testing. Our advisors for this project were Dr. Susan Levy and Dr. Benjamin Basil. Turbine Controls Inc., or TCI, is a company located in Miramar, Florida, that repairs and overhauls air turbine starters. Starters are the power source to aircraft engines, and during testing they're connected to a flywheel with a certain moment of inertia to simulate the inertia of the aircraft engine. Different starters require different inertias. Therefore, TCI is currently limited by their two inertia system, and thus the goal of this project was to design a dynamometer that would allow various inertias in order to test different starter sizes. A dynamometer is a device used to test power sources such as starters, engines, and motors. And during testing, the unit is connected to the dynamometer, and it drives the dynamometer. In this way, the dynamometer resists the torque provided by the unit, and the load applied on the unit is controlled at the dynamometer. The essential features that a dynamometer should have are the means to control and measure torque, power, and speed. And we considered 3 dynamometer types for this project, out of which one was selected after comparing their features. Based on TCI's budget, the inertia dynamometer was selected. And after reviewing 15 different starters, we selected 3 that correspond to the lowest, highest, and middle inertias observed in the range of starters, and at the same time correspond to the lowest, highest, and middle speeds observed in the range. The key test parameters that we considered were torque, speed, and acceleration. And finally, it was also important to demonstrate the repeatability of the system, since test data is to be provided by the dynamometer. When designing a dynamometer, it is important to ensure that it will be able to reach maximum speed, torque, and power. And the manuals for starters only provide certain information, which includes the maximum speed it should reach, which is the cutoff RPM, the time it should take to get to that speed, and just the last few seconds of the RPM versus time plot. Therefore, in view of this limited amount of information, 2 approaches could be taken. The first one consists of taking the overall average, just knowing the maximum speed and when it occurs. And the second approach consists of taking the average of the last few data points that are known and take that as a representation of the rest of the curve. After knowing the percent of error associated with each approach, the second approach was taken. And in this way, as shown on the table, for the 3 inertia selected, the angular speed, acceleration, and torque were calculated, and these parameters were used throughout the design process. The initial design alternatives proposed consisted of concentric rings as flywheels. However, difficulties seen in these alternatives include the complexity of fluid behavior around the system, the difficulty in manufacturing them, and also the lack of a good locking mechanism. Therefore, the final design consists of concentric cylinders instead of rings. And thus, this helped mitigate the previous problems. And as shown on this figure, we have the largest, medium, and smallest flywheels. And to visualize how it works, the largest flywheel would be now engaged. If a lower inertia is required, it could be opened up towards the sides, leaving the middle flywheel engaged. And if an even lower inertia is required, then the middle flywheel can be opened up, leaving the smallest flywheel engaged.
So one of the strongest and densest grades of steel was selected as the material for this system. And we first had to calculate the maximum centrifugal stresses allowed at any given point in the system. So that depends on the ultimate tensile strength of the material, the radius, and the RPM at which it will run. The maximum linear velocity at any given point in the system is 1200 feet per second. We then had to establish factors of safety for both stress and velocity. And we know that the flywheel stress increases with the square of velocity. That's why we calculated for the worst case scenario, which is the largest inertia, both because it has the largest RPM and the largest radius. Relatively low factors of safety at 1.2 and 1.44 were selected for the system, but that's not a problem since all testing will be conducted in a very well supervised environment. We know from the inertia relations that radius affects inertia more than mass. That's why the radius has to be large enough to generate the most inertia, but small enough in order to keep these safety factors. After iterations, a radius of 13 inches was selected, and the mass required in order to reach to this 69 slug feet squared inertia system is 114 slug. We then had to calculate the volume in order to come up with a flywheel length of 23 inches. Important assumptions in the design include that none of the flywheels are hollow and that any drilled holes will be filled and replaced with similar mass and volume. Material removal due to balancing and shaft clearance is also negligible. This flywheel must now be hollowed out, and the interior radius and length are determined by the outer dimensions of the inner flywheel. Now for the middle flywheel, we have to keep the radius large enough to reach this inertia, but small enough in order to retain lip strength on the outer flywheel as well as fit inside it. After iterations, a radius and length of 12 and 10 inches respectively were selected for the system. This flywheel must also be hollowed out. Now for the smallest flywheel, we did the same design process, and we ended up with a 9 and 6 inches for radius and length respectively. However, this flywheel is not hollow because it's closest to the shaft and was press-fitted onto it. For the shaft design, the length had to keep as short as possible in order to decrease deflection, but it must be able to accommodate all three loading cases. That's why the three of them were calculated, and we had to go with the worst case scenario, which was about 3 feet. For the diameter, we had to make sure that it was big enough in order to prevent torsion and deflection and be able to transmit the given power. After iterations, a diameter of 4 inches was established. Shaft whirling, which is the rotation of a plane by the bearing centerline and bent shaft, is governed by inertia, spring, and damping forces. So these were taken into account during the design process. And in order to decrease rotor imbalance, which is what causes eccentricity, we balanced the flywheels using the 1940-1 standard. A critical speed of 1700 RPM was calculated, which is when the frequency of rotation equals the natural frequency. That's when large deflections occur, and that must be avoided. For the prototype construction, we selected aluminum 6061, which is what TCI has in-house, and the largest diameter cylinder is what determined the maximum diameter for our systems. Instead of using an air turbine starter as a power source, we used an electric motor. Above we can see the parameters for the largest, medium, and smallest flywheels respectively, but the most important aspect of this slide is to see that all the systems behave and work just like the full-scale model, however, of course, in a much smaller scale. We use the same approach for the shaft design to get a diameter and length of 1 inch and 1 feet respectively. A critical speed was calculated at 2900 RPM, and in order to prevent shaft whirling, we found the eccentricity via testing and math. We also used the same industry standard to balance the flywheels.
So, in order to meet one of the most important safety standards, which is to provide safety to the user, we went ahead and we designed a containment shield. From this containment, we had to calculate the boundary layer thickness that develops around the flywheel as it spins. And from this equation, we can see that that thickness is about 2.7 millimeters. And based on that thickness, we can determine the maximum damping torque that occurs in the system. So using that value on this other equation, we determined that the damping torque is about 11 newtons millimeters. So based on that design, we conduct an impact analysis from which we took two approaches. One is doing calculation by hand and using ANSYS for simulating the impact. And these tables displays the results for both approaches. We can see that both results are similar. However, we have a margin of error of about 11–12%, and we attribute that margin of error to the fact that when you do calculations by hand, you don't take into account how much energy is dissipated throughout the system as the flywheel impacts the wall. We also use ANSYS to carry out a structural simulation based on torque and velocity, from which we were able to obtain the maximum stress and the maximum strength and deformation on the flywheel as it spins. And in order to know how much the total unit will cost, we did a cost analysis. These tables show the cost for each individual part, and we came out with a total cost of about $3,500. And in order to test the unit, we also designed a test plan, which consists of two parts. The first part is using the electric motor, from which we can determine the angular velocity response with respect to time. And the second part consists of using a balancing machine where we can get the eccentricity data for each flywheel. These two pictures show the equipment that was used to carry out the test. Here we want to show a quick video how we conduct the first part of the test. So in this particular case, sorry for the image, we use the smallest flywheel and the test monitor is displaying the results. So based on those results, we were able to obtain the angular velocity response, and we can see from these trend lines how their respective slope is changed. And this slope is very important because this is representative of the acceleration of each rotor. So based on those results, we were able to determine that the largest flywheel has the slope with the smallest value, and that the smallest flywheel has the slope with the largest value. And this confirms that the inertia has an effect on the acceleration. And also from the standard deviation, we could also confirm the repeatability of the system. From the eccentricity results, we were able to obtain the amplitude of the rotational motion, and we were able to compare those amplitudes to the maximum static deflection. So from the test, we can conclude that as the inertial load is increased on the flywheel, the time that it takes to attain the maximum speed is also increased. And from the second part, we can conclude that the dynamic deflection is larger than the static deflection. And as the inertia is increased, the amplitude of the rotational amplitude is also increased. However, that amplitude is not big enough to lead to larger vibrations on the system. And also, those amplitudes do not affect the repeatability of the system. So one of the things that we took into consideration for designing the unit was the health and safety of the user and the impact that it has on the environment, the assembly or disassembly of the unit, the maintenance of the system, the manufacturability, and the impact that it has, the economic impact that it has on the company.
In preparation for the tasks that were needed for the completion of this project, there were assigned timeframes, and the responsibilities were divided among the team members. And taking into account global design aspects, the FIA and the EASA are the main agencies that provide regulations for air turbine starters. Other organizations also provide standards, from which the main ones used were balancing tolerance standards. And in conclusion, from the project, we can see that we were able to put together a thorough analysis, including different branches of mechanical engineering. So going from structural engineering to vibration analysis, fluid analysis. Therefore, we were able to provide a thorough analysis for the concentric cylindrical flywheel system. And we were able to show that the difference in inertias did have an impact on the acceleration of the power source that was tested. In addition, the next step would be to be able to compare what the prototype is doing and what should be expected of the real size application. And for this, we would be needing to measure and control the torque parameter. And so by the end of this, we were able to establish a relationship between TCI, the company, and FIU. Therefore, more projects such as this one could arise in the future for future senior projects. From this project, immediate next steps could be taken into another project, starting with the consideration of the torque parameter, going into considering a brake system, a crane system, or automizing data acquisition. We would like to acknowledge TCI faculty members and TCI personnel and FIU faculty members as listed on this slide. And we would like to take any questions. And we're going to show a little bit how this works.
So just to show the simplicity of the design, we can see 3 bolts on each side. However, these were already taken out. So it's as easy as taking 3 bolts per side and just sliding off the flywheels onto the side to change the inertia of the system to whatever you decide.
And the lines shown here were there for the balancing process to make sure that the amplitude of the motion fall within tolerance. Thank you.
Does this test apparatus need to be certified or in calibration at any time, like monthly, annually?
So when it comes to maintenance, definitely we think after going through the balancing process that a regular schedule should be followed for balancing, because little parts such as the screws and stuff like that and manipulation can bring it out of balance. So therefore, definitely balancing would be one of those maintenance parts. Now, for the real application, I would say that the time for maintenance would come with experience, because we wouldn't know exactly how long unless we were operating this for months and know how long it requires, how often it requires a balancing.
Thanks.
Done?
Yeah.
Okay. Would you have to get FAA approval for testing procedures in order for them to use it
Yeah,
on a
they-
regular basis?
Yeah, that's what the company is, when they were ones who treat that, let's say, per se. We don't have any contact with FAA while doing this.
So they're taking.
So
Yeah.
they take care of that,
While
and we
we
just
there-
give them the design.
While we were there testing, doing our prototype test, they had the FAA visiting actually the location, so I'm pretty sure they would need to be approved by the FAA. They were showing them one of their other testings, so that would probably be the case with this application.
No, the smaller cylinder is one that's permanently attached to the shaft, and the rest just slide on top
Correct.
of it. Now that you slid that one over there, when it's being tested, is there anything to stop it from sliding back while it's being
Oh,
run?
yes. Washers go onto this screw in order to hold this up. This was
Oh.
just quickly done to demonstrate how fast it is to change the inertia.
We would lock the nuts
The nuts.
to hold it, and so that the flywheel is not resting on the shaft, so that the weight, the load of this flywheel is not affecting the inertia of the
I
system.
see, okay,
So there's a clearance between the shaft and
okay.
the bore of each of the flywheels.
Yeah, because I just slid that, I'm like, well, wait a minute. Okay. I'm done.
Did you guys deal with the interfaces between the motors that AAR works with? Like, did you consider that? Because from what I've seen, a lot of these motors have completely different interfaces in terms of how you connect them to a shop. And it's a pain to have to design specific tools for each one. So either you make a specific mounting plate for a specific set, and then you kind of take it from there. Or did you guys address that at all in your design, or is that something?
Well, TCI has a current system that they use, but they're very limited just from this aspect, which is the flywheels and the inertia. So we didn't take that into consideration because they explained to us what we had to do, already assuming that was done on their part.
So they do have on their current system the connections where for different spline connections
Yeah.
for the different inertias. So I would imagine because the output shaft of each starter would be different in size. So they have the adapters for that, and that would be the case to adapt that to this design. Make sure that they are attachable.
For this particular case, we don't have like any extra, let's say, things to interface. For example, we didn't use like any gears interfaces to increment ratios. We only use the copter. That's the only thing. We didn't have to take into account all those interfaces as I was talking to you before.
Just a comment regarding your graphs you're plotting on the, when you were looking at linear, taking a best fit line to your data.
Yeah.
I would just say make sure to include the R² value and give us a measure of what that fit was. In terms of scaling, you know, the scale could be very large and you could actually have a lot of variability around that line. That may give you actually a worse fit than you can visually tell.
Well, yeah, that's a great recommendation. Thank you for that. This was just shown like this in the presentation in order to avoid too many graphs. But in the report, everything is more thoroughly explained.
There's no R² values in the report.
Oh, no, the R squared, we're missing that.
Right. No, that's why I ran it.
Thanks.
Good job.
All right, thank